yourself out under a dark sky that is so clear and so pristine that you can see the Milky Way spanning from horizon to horizon, aglow with the light of 100 billion stars. You don't have to imagine that. You live in Chile. You can go out on any moonless night away from the city and see the sky so beautiful it's unrivaled from anywhere in the earth. It's almost as if you could reach out and touch the stars. The skies here in Chile are not just beautiful, they're a laboratory for addressing some of the most profound questions that we face. My name is Patrick Mccarthy. I am the director of what we call NSF NOIRLab. We're the United States National Science Foundation's National Laboratory for Optical Astronomy. You might know us as Aura Observatory in Chile, or Cerro Tololo, or just Tololo, but I'm here to tell you that we are much more than just Tololo. When I decided to become an astronomer, I was only 9 years old, and I did not realize that I would spend most of my career here in Chile. I've been coming here for 40 years now, and I consider myself extraordinarily privileged. This is the place to do astronomy, and I've been blessed with the opportunity to come here for so many years. And there you can see me with my first telescope. Very embarrassing, but that's how it goes. So, the unique geography of Chile, of its coastal mountains and high deserts, have attracted people from all over the world to come here to build observatories and to do astronomy. Aura, which is a consortium of universities primarily in the US, entered into an agreement with President Eduardo Frei, the first one, and the University of Chile in the 1960s to build the Cerro Tololo Inter-American Observatory. In the 1970s, we built the Victor Blanco telescope, the largest telescope in the Southern Hemisphere. In 2000, we finished the Gemini telescope, an 8-meter telescope. And this year, we will commission the Vera C. Rubin Observatory, named after the discoverer of dark matter. International organizations, including the US National Science Foundation, the Carnegie Institution, the European Southern Observatory, the country of Japan, have collectively invested roughly $5 billion here in Chile, and we partner with Chilean institutions to enable cutting-edge research for people around the globe. The International Observatories spend about $100 million a year on operations. We employ more than 1,000 staff, the majority of whom are Chileans in roles of technical managerial roles across the whole organization. 10% of the observing time on all of our telescopes goes to scientists at Chilean institutions, and they can do whatever they want with it to pursue their own scientific goals. These investments, the dedicated staff, the technical knowledge of our Chilean team, have made Chile the focal point for astronomy on the surface of the Earth. The stable political situation in Chile, the growing economy, the growing technical workforce makes it an ideal international partner. Astronomers, we ask really simple questions like, where am I? How did we get here? Are we alone in the universe? But these simple questions have led us on an amazing journey of discovery, and it's by no means over. In fact, as I will tell you, we're starting a new chapter shortly. If we take the entire 13.8 billion year history of the universe and map that onto 1 year, with the Big Bang happening at January 1st, we'd find that the sun formed in about August. The Earth cooled in September and October. The first humans would appear on December 31st at about 8 minutes before midnight. Quite recent. Hubble's discovery of the expanding universe would have happened 1/2 second before midnight. So astronomy to us is a relatively recent discovery. It might seem hard to believe, but everything that we can see and touch in the world, whether that's the stars, the planets, rocks, people, we only constitute about 4% of the total contents of the universe. The nature of the remaining 96% is a mystery. About 68% of that is what we call dark energy. It's a mysterious substance that is driving the universe to expand at an ever-increasing rate. We don't know what it is, we can't see it, but we can see its impact on the visible parts of the universe. Dark energy was discovered here in Chile and it was recognized with a Nobel Prize in 2011. The remaining sort of 38% or so is what we call dark matter. It's what holds galaxies together and what gives the universe its character of islands of stars in a vast sea of seemingly empty space. It turns out it's not really empty. When I was starting in astronomy, we knew nothing of dark energy. We were just starting to suspect that there are parts of the universe that we can't see, but we all had one clear dream, which was to answer the question, are we alone in the universe? Is there life outside of the Earth, outside of the solar system? And I think as long as people have looked up at the stars, they've asked themselves, are there others out there? For a long time, this was just science fiction, but now it's actually mainstream scientific research. The first planets orbiting other stars were discovered here in Chile, and that was recognized with the Nobel Prize in 2019. And now we know that planets are quite ubiquitous. A good fraction of stars like the Sun not only have planets, they have planets in what we call the habitable zone, the distance from their star where water, if it's present, would be in a liquid form, an essential ingredient to life. The detection of life beyond the Earth or beyond the solar system would not only be one of the most profound scientific discoveries, it would change the way we look at ourselves, the way we look at the heavens, the way we think about the Earth. And it could happen in your lifetime. It's real science now, it's not science fiction. So these questions are what excites us about astronomy. It's about what we do at NOIRLab. We enable great discoveries. We operate observatories around the world. We write software. We produce data. And together, we help people address these most pressing and frontier questions in astronomy, whether it's the nature of black holes, dark matter, the overall evolution of the universe itself, or even looking at our own backyard and understanding the properties of the solar systems and all the things that inhabit it. You might ask, well, what limits our ability to do astronomy? And there's a few things. First is how much of the sky we can see at any one time. More sky means more science. The second is how faint we can observe. That's what leads us to build big telescopes. But a critical factor is the quality of the skies above us. And there's only a few places on the Earth, Chile being the foremost, in which the skies have the absolute requisite quality. Just outside of La Serena, there's the Cerro Tololo Inter-American Observatory. That's home of the Blanco telescope and its world-leading wide-field dark energy camera, built to study dark energy, but it is still the most powerful wide-field imager on the planet for about another 10 months. These pictures just show you some example of the beautiful and useful images that the Blanco takes every night, and it's the workhorse for much of U.S. and international astronomy. But about 8 kilometers away as the condor flies is our next generation observatory, the Rubin Observatory on Cerro Pachon. Rubin will completely eclipse the Blanco and any other telescope on Earth, in space, or on the drawing board in its ability to observe the entire sky. Every 3 nights, Rubin will map the complete sky, the sensitivity of an 8-meter telescope. It's our newest and most exciting tool, and it's coming online very soon. Later this year, Rubin will begin a 10-year legacy survey of space and time. It will map the sky to measure the evolution of dark energy, the distribution of dark matter, and look at the dynamical universe. For millennia, we've thought of the sky as the fixed stars. They never change, and the wandering planets. But now we know the universe is a very dynamic place. All the stars in the sky move relative to each other. Many of them vary in brightness. A few of them occasionally explode and make supernovae that help produce some of the chemical elements and leave behind neutron stars or black holes. A few stars, unfortunately, end their lives by wandering too close to a black hole where they're shredded and make a beautiful cosmic fireworks display for a short period. Occasionally, 2 neutron stars, the remnants of those supernovae, will merge together, creating a burst of gravitational waves, build a black hole, and they will produce the chemical elements that we think are most precious and useful: gold, platinum, silver, and others. Those are created when neutron stars collide with each other. The Rubin Observatory will see all of these transient phenomena, many of them per night, and they will inventory everything in our solar system down to the smallest asteroids, including those that pose a risk to Earth that could potentially impact us. About 5 times a year, we will detect interstellar visitors from outside our solar system. These are bodies that were ejected from other planetary systems, sent to wander aimlessly through the galaxy. They will pass through the solar system, and we'll have just a few days or a week to study them before they go on their way through the darkness of space. The Rubin Observatory has some really novel technology. It has a very compact optical system that makes it like a super wide telephoto lens. You can see a lot of the sky, and the telescope is very compact because it has to move every 30 seconds and take another picture without shaking, without any distortion. But the heart of the whole observatory is the world's largest digital camera. It kind of looks like the lens on your handheld camera, but it's a lot more complex. It's about the size of a small car. It weighs about 3 tons. It has the largest lenses ever built, a real technical feat. But its detector, its focal plane, has 3.2 billion pixels. It's a 3 gigapixel camera, if you can imagine that. That's what makes it so powerful, and it took quite a lot of effort to build it, to bring it to Chile, to install it on the telescope, and it's now ready to go. It would take more than 400 Super HD television screens to display one image from Rubin, and we'll take 1,000 of those a night, every night, for 10 years. So to give you some idea of the power of this is your favorite constellation, Orion, upside down for us northerners. And Rubin will map the entire constellation of Orion, where stars are being formed rapidly right now, in just 20 minutes. It would take a year to do that on current telescopes, and it will do this over and over and give us a dynamical view of where stars are being formed in the Milky Way. In 1 year, Rubin will collect more data and share that with the world than every other telescope in the history of astronomy combined. That's quite a game changer. But Rubin is really built to do this dynamical study, so when a star either moves or gets brighter or does anything unexpected, Rubin will detect it, and will do this about 10 million times per night, and it will tell anyone in the world in 4 minutes, something happened, here's where you can go look at it, so they can use telescopes either that we operate in Chile or elsewhere to go follow it up. As we heard yesterday, scientists at Chilean universities are writing very sophisticated software using AI to sort through those 10 million events a night to figure out which ones do I want to study. And without that software, we would be lost. That's one of Chile's great contributions to the project. Rubin superpower is its wide field camera, but there are other telescopes being built here that aim to go super faint and to look in great detail at planets around other stars. In the north of Chile, the European Southern Observatory is building the European Extremely Large Telescope, and it is extremely large. Another group is building what's called the Giant Magellan Telescope just north of La Serena at the Las Campanas Observatory. It will have 7 mirrors, each of which are 8 meters in diameter, together giving it the collecting area of a 25-meter telescope. This will allow it to produce images that are 4 times sharper than those coming from the James Webb Space Telescope and 10 times sharper than the beautiful pictures that have come from Hubble. These telescopes will be used to measure the atmospheres of other planets to look for life. That's one of their key missions, and people are building them here in Chile because this is the place to be. So all of this sounds great. There are some clouds on the horizon, and our challenges now are, how do we keep these beautiful skies clean and pristine? There's a risk from the industrialization of space, the very large number of low Earth orbiting satellites, and from the proliferation of outdoor light pollution due largely to low-cost, high-intensity, high-color temperature light-emitting diodes, which are ubiquitous and are diluting the night sky and making it hard to see things, while these satellites make streaks in our beautiful images. It's not just the research observatories that are feeling this impact, but the private tourist observatory business, which is flourishing in the Elqui Valley and elsewhere, are seeing the impact of light pollution in the satellites, and it's bad for business. Fortunately, the government of Chile is far-thinking. They are understanding the importance of astronomy both professionally and commercially, and they have passed legislation to protect the skies. In October of last year, a new lighting norm came into effect, and we think that will help sustain Chile's leadership both in professional and touristic astronomy. We at NOIRLab, we work with the local communities around the observatories to help them understand how to best serve municipalities, citizens, and businesses while keeping the local skies dark. This is not just about astronomy, it's really also about protecting the cultural heritage of the areas around the observatory. It's hard to think that entire generations are growing up now who have never seen the Milky Way because the skies in their cities are just too bright. So the ongoing investments here in Chile, the great support of the government, the growing and diverse technical workforce in Chile have made Chile the focal point for astronomy in the world. In the 2030s, something like 70% of all the observing power on the planet will be here in Chile. At NOIRLab, our mission is to uncover our cosmic origin, understand the universe, understand our place in it. We help people make breakthrough discoveries. You might ask, with all that's going on in our lives and all the problems in the world, why should we care about what is up there? But it gives us more than just science. It gives us a perspective on our lives, on the vastness of the universe, and the very special place that we live within it, called the Earth. It's been a tremendous century of discovery in astronomy in the Americas, both North and South. Imagine what the next century will bring. The story of preserving Chile's skies is really a story of partnerships, of cooperations, of perseverance, and it's a reminder when we look up at the sky, there's something that's much bigger than all of us and yet unites us. It's one sky for all of us. So as we move ahead, let's work together to cherish and protect these skies and ensure that the next generation is inspired with the same wonder that I was when I was 9 years old or when I first came to Chile, because together we can unlock some of the most profound mysteries of the universe and answer perhaps the most profound questions, are we alone in the universe? And it all starts right here in Chile. Gracias.